Right now, as you listen to this, an invisible force is shifting on the face of our sun. A colossal wound, a magnetic maelstrom so vast it could swallow 10 Earths whole, has just rotated into view. This isn't just another sunspot, it's a monumental shadow, a raw scar on our star's blazing surface, and for the first time in over a decade, its gaze is locked directly on us. Every space agency, every astronomer, every geophysicist on Earth holds their breath. Because what this behemoth unleashes in the coming days could fundamentally rewrite the script of our technological civilization, they are calling it Active Region 4294 through 4296. A designation so complex officials had to split it into 3 separate numbered groups just to categorize its sheer scale. Amateur astronomers are reporting they can see it with the naked eye using nothing but a proper solar filter. 5 Earths tall, 5 Earths wide, and it is pointed directly at us. The question no one wants to answer aloud is simple. What if this thing fires? What if the largest sunspot in 10 years decides to unleash its fury while Earth sits squarely in the crosshairs? By the end of this journey, you will understand exactly what we're facing, why scientists are losing sleep over the next 72 hours, and what a worst-case scenario would actually look like for every person on this planet. Some of what I'm about to tell you will sound like science fiction. I promise you it is not. Before we dive in, if you enjoy these deep dives into the cosmos, hit like and subscribe so you never miss an update. Now tell me in the comments where are you listening from and what time is it there. What you need to understand first is that our sun is not a stable, peaceful ball of light. It is a thermonuclear furnace, a churning sea of plasma held together by its own immense gravity, where temperatures exceed 15 million degrees at the core. Magnetic field lines twist, tangle, and snap with a violence we can barely comprehend. Sunspots are the visible evidence of this internal war. They appear as dark regions on the solar surface, not because they are truly cold, but because they are cooler than their surroundings, typically around 3,500 degrees C compared to the 5,500 of the normal photosphere. That temperature difference makes them appear black against the blazing backdrop. But make no mistake, a sunspot is still hot enough to vaporize anything we have ever built. The sunspot that merged on December 1st, the one designated AR4294 through 4296, is not ordinary by any measure. Patricia Leon, an amateur astronomer observing from Santiago, Chile, described it as enormously huge and complex, requiring more than 2 days just to rotate entirely past the eastern limb of the sun. 2 days. Think about that. The sun rotates, and this single feature took 48 hours to fully come into view. Leon noted something else that should concern anyone paying attention: the delta magnetic component. In solar physics, a delta configuration means that opposite magnetic polarities are packed together in the same penumbral structure. Umbra of opposite polarity sharing the same shadow. This is the magnetic equivalent of 2 colossal tectonic plates grinding against each other. Pressure builds tension, accumulates, and eventually something has to give. The classification system for sunspots tells us exactly how worried we should be. Alpha regions have a single dominant polarity, simple and stable. Beta regions show a bipolar structure with distinct positive and negative areas, more dynamic but still manageable. Beta-gamma configurations indicate that the positive and negative polarities are so intermixed that no clear line can be drawn between them. And then there is beta-gamma delta, the most complex and dangerous classification, where those intertwined polarities exist within a single penumbral structure. AR4294 has been classified as beta-gamma delta. It is magnetically speaking a coiled spring waiting to release its fury. What makes this particular moment so significant is context. We are deep within solar cycle 25 and it has been a wild ride. When this cycle began back in December of 2019, the official prediction panels expected a weak and quiet maximum similar to the underwhelming cycle 24 before it. They projected a peak of around 115 sunspots sometime in July of 2025. They were wrong. By 2022, activity was already outpacing predictions. By 2023, NOAA had to revise their forecast upward admitting that solar maximum would arrive earlier and stronger than anyone anticipated. By October of 2024, scientists confirmed that solar maximum was already underway, potentially having started as early as 2 years before anyone officially acknowledged it. The sunspot counts in August of 2024 reached the highest level since September of 2001. This is not supposed to be happening, and yet here we are. The Sun has been throwing X-class flares with increasing frequency. On November 11th, active region 4274 produced an X5.16, the strongest flare of 2025 and the 6th largest of the entire solar cycle. It released a coronal mass ejection travelling at 1950 km/s, so fast that NOAA issued a rare G4 geomagnetic storm watch. Just 2 weeks later, another region produced multiple X-class events in rapid succession, each one a reminder that our star is operating at a level of intensity that defies the predictions of every major space weather institution. Now the largest sunspot in a decade has rotated into view and it's already flexing its muscles. On the same day, AR4294 became visible. Another newcomer designated AR4299 fired off an X1.9 flare at 2:27 UTC. The eruption was captured by NASA's Solar Dynamics Observatory, a towering structure of plasma and energy breaking over the limb of the Sun like a slow-motion explosion frozen in ultraviolet light. The radiation reached Earth in 8 minutes, ionizing the upper atmosphere and triggering an R3 radio blackout across Australia. Aviation communications went dark. Maritime signals dropped out. For approximately 30 minutes, an entire continent lost high-frequency radio capability because of an event that originated 93 million miles away. That flare did not come from the giant sunspot. It came from a smaller region nearby, almost as if the Sun was sending a warning shot, a preview of what the main event might deliver. Coronagraph imagery from the Solar and Heliospheric Observatory revealed a rapid partial halo coronal mass ejection associated with the blast. Billions of tons of magnetized plasma hurled into space at tremendous velocity. The good news, if you can call it that, is that this particular ejection was not aimed at Earth. It blasted off the northeastern limb and sailed harmlessly into the void. But the geometry is changing. Every hour the Sun rotates slightly, and every hour AR4294 turns a little more toward our planet. The coming days are critical. NOAA's Space Weather Prediction Center has issued their bulletin for December 1st through 5th, forecasting a 70% chance of M-class flares and a continuing possibility of additional X-class events. They anticipate active to G1 minor storm conditions around December 3rd as a coronal hole high-speed stream sweeps past Earth, the same recurrent feature that produced strong solar winds back in early November. By December 4th, if timing aligns poorly, we could see G1 to G2 conditions possibly reaching KP7 at peak. Auroras might dance as far south as Toronto, Chicago, Boston and Melbourne. Beautiful, certainly, but beauty often masks danger. What concerns scientists is not just the immediate forecast, but the immense potential for chaos. AR4294 is not simply large, it is magnetically primed. The delta configuration means energy is being stored in twisted magnetic loops that could release at any moment. When those loops reconnect, when the magnetic tension exceeds the threshold, the plasma can contain. The result is a solar flare, an explosion that can release energy, equivalent to billions of nuclear weapons detonating simultaneously. The largest flares, the X-class events, can ionize Earth's atmosphere and disrupt communications within minutes of occurrence. But the flares themselves are only part of the story. The real threat comes from what often follows. Coronal mass ejections are the heavy artillery of solar weather. Unlike the electromagnetic radiation of a flare, which travels at light speed and arrives in 8 minutes, a CME is a physical mass of charged particles and magnetic field. Billions of tons of solar material flung outward at speeds ranging from 250 kilometers to over 3,000 kilometers. Depending on the velocity, a CME can reach Earth in as little as 15 hours or take several days. When it arrives, it collides with our magnetosphere, the invisible magnetic shield that has protected life on this planet for billions of years. Under normal conditions, the magnetosphere deflects most of the incoming particles, channeling them toward the poles, where they create the shimmering curtains of the aurora. But when a CME is powerful enough, when its magnetic field orientation is just wrong, it can compress the magnetosphere, distort it, and in extreme cases temporarily punch through. That is when things get truly dangerous. That is when the modern world discovers just how dependent it has become on systems that were never designed to withstand the fury of our own star. The power grids, the satellites, the GPS networks, the internet infrastructure, all of it connected, all of it vulnerable, and most of it running on the assumption that space weather is someone else's problem. For now, the Sunspot watches and waits. It rotates a little further into view, with each passing hour its dark heart aimed increasingly at the planet where 8 billion people go about their lives blissfully unaware that a wound on the sun could reach across the void and touch them. The next few days will tell us whether AR4294 is merely impressive or genuinely dangerous. Scientists are hoping for the former. They're preparing for the latter. And somewhere in observatories around the world, instruments are recording every fluctuation, every brightening, every hint that the magnetic tension is about to break. The sun has kicked off December with a statement. Whether that statement becomes a warning or something far worse remains to be seen. What happened in 1859 when a similar configuration unleashed an event that would bear the name Carrington offers a chilling glimpse of what might be possible. But that was a world of telegraph wires and gas lamps, a world that had no idea how dependent its descendants would become on the very technologies most vulnerable to solar assault. The rules have changed, the stakes have multiplied, and the sun does not care. When the sun spoke to Australia at 2:27 Universal Coordinated Time on December 1st, 2025, it released a burst of electromagnetic radiation so intense that it crossed 93 million miles of empty space in approximately 8 minutes and 20 seconds. By the time the first photons reached Earth, the event was already over on the solar surface. But for the people on the sunlit side of our planet, the consequences were just beginning. Australia bore the brunt of it. Across the continent, high-frequency radio communications simply stopped working. Aviation signals dropped into static. Maritime operators found themselves suddenly isolated, their equipment functioning perfectly, yet receiving nothing but noise. For approximately 30 minutes, one of the most technologically advanced nations on Earth experienced a communications blackout, triggered by an explosion on a star. This was an R3 event on the NOAA radio blackout scale, classified as strong. The scale runs from R1 minor through R5 extreme. An R3 blackout means wide area degradation of high-frequency radio communication and loss of radio contact for about an hour on the sunlit side of Earth. Navigation signals experience errors. It is not catastrophic. It is not civilization ending. But it is a stark reminder, a tap on the shoulder from the cosmos, that the infrastructure we take for granted operates at the pleasure of forces far beyond our control. The flare itself was classified as X1.9. To understand what that means, you need to understand how solar flares are measured. The classification system uses letters A, B, C, M, and X, with each letter representing a 10-fold increase in energy output. A-class flares are barely detectable above the background radiation of the sun. B-class flares are slightly stronger but still negligible in terms of Earth effects. C-class flares are common and can cause minor radio interference at high latitudes. M-class flares are moderate, capable of causing brief radio blackouts in polar regions and occasionally at lower latitudes. And then there is X-class, the most powerful category, where the numbers after the letter indicate magnitude within that extreme tier. An X1 flare is 10 times more powerful than an M1. An X10 is 10 times more powerful than an X1. The scale technically has no upper limit, though the strongest flare ever recorded was estimated around X45, a monster that erupted in November of 2003 and saturated the sensors designed to measure it. An X1.9 then sits comfortably in the lower range of the extreme category. Powerful enough to cause significant radio disruption, strong enough to ionize the upper atmosphere and alter the propagation of radio waves, but not powerful enough to threaten satellites or induce dangerous currents in power lines. Not yet. The flare that hit Australia was, in the grand scheme of solar violence, a moderate event from an extraordinary source. The concerning part was not the flare itself, but what it represented. A new active region, still emerging over the solar limb, still partially hidden from Earth view, had already demonstrated it was capable of X-class eruptions, and behind it, rotating into ever more direct alignment with our planet, sat the largest sunspot complex in 10 years. Think about that geometry for a moment. The Sun is a sphere rotating on its axis roughly once every 25 days at its equator. Active regions emerge, grow, and decay over periods of days to weeks. As the Sun rotates, features on its surface sweep across the visible disk like landmarks on a slowly turning globe. A sunspot on the eastern limb is not aimed at Earth. Its flares and ejections are directed sideways off into space at an angle that poses little threat to our planet. But as the Sun rotates, that same sunspot moves across the disk toward the centre, and when it reaches the central meridian, anything it releases is pointed directly at us. AR4294 emerged on the eastern limb on December 1st. It will take approximately 7 days to cross to the western limb. Sometime around December 4th or 5th, it will pass through the zone of maximum geo-effectiveness. The region where any coronal mass ejection it produces will be aimed squarely at Earth, the X1.9 flare that blacked out Australian communications came from AR4299, a smaller region travelling just ahead of the giant. It was like a scout firing a warning shot before the main army arrives. The flare peaked at 9:49 p.m. Eastern Standard Time on November 30th, which translates to the early morning hours of December 1st in Universal Time. NASA's Solar Dynamics Observatory captured the eruption in multiple wavelengths, each revealing different aspects of the violence. In extreme ultraviolet light, the flare appeared as a brilliant white flash against the dark corona, a localized explosion of energy that briefly outshone the entire surrounding region. The imagery showed towering loops of plasma magnetic field lines made visible by the superheated gas trapped within them, arcing hundreds of thousands of kilometers above the solar surface. Associated with the flare was a coronal mass ejection captured by the coronagraphs aboard the Solar and Heliospheric Observatory. SOHO, as it's known, sits at the L1 Lagrange point, a gravitationally stable location, about 1.5 million kilometers sunward of Earth. From there, it maintains a constant watch on the Sun, its coronagraph instruments blocking out the brilliant solar disk to reveal the faint outer atmosphere where CMEs become visible. The December 1st ejection appeared as a rapidly expanding halo of brightness, a partial halo indicating that the material was being flung in Earth's general direction, but not directly at us. Analysis confirmed that the CME was not Earth-directed. It would sail past a bullet that missed. But the near miss contained a crucial lesson. The speed of that ejection was significant. It expanded rapidly, indicating high velocity. The kind of speed that would deliver a CME to Earth in under 2 days if the geometry had been different. Fast CMEs are dangerous CMEs. They compress the solar wind ahead of them, building up a shock front that amplifies their impact when they finally collide with a planetary magnetosphere. The fastest CMEs on record have reached Earth in as little as 15 to 18 hours. The Carrington Event CME, the benchmark against which all solar storms are measured, made the journey in approximately 17.12 hours. Typical CMEs take 2 to 4 days. When you see a fast ejection, you pay attention even if it is not coming your way this time. The radio blackout over Australia demonstrated something else that often gets lost in discussions of space weather. The effects are immediate but temporary for flares. Electromagnetic radiation travels at light speed. There is no warning. By the time you detect the flare, the radiation has already arrived. But the ionospheric disturbance fades relatively quickly once the flare ends. High-frequency radio communications were restored within an hour. No permanent damage occurred. No equipment was destroyed. The blackout was an inconvenience, not a catastrophe. This is important to understand because it distinguishes flare effects from CME effects. Flares are fast and fleeting. CMEs are slower and potentially devastating. A flare is a flash of light. A CME is a physical punch. The ionosphere, that layer of Earth's atmosphere between roughly 60 and 1,000 kilometers altitude, is where this interaction plays out. Under normal conditions, the ionosphere contains enough free electrons to reflect certain radio frequencies back to Earth, enabling long-distance communication without satellites. This is how shortwave radio works, how aircraft over oceans maintain contact with controllers thousands of miles away, how ships communicate when they are beyond line of sight of land-based towers. The ionosphere acts as a mirror bouncing signals around the curvature of the planet. But when a solar flare dumps X-ray and extreme ultraviolet radiation into the upper atmosphere, it ionizes far more atoms than usual. Paradoxically, this over-ionization degrades radio propagation rather than enhancing it. The signals get absorbed instead of reflected. The mirror becomes a sponge. What Australia experienced was a textbook demonstration of this process. The flare enhanced ionization on the day side of Earth, and Australia happened to be in daylight at the moment of peak radiation. Aircraft in flight would have noticed degraded or absent high-frequency communications. Maritime vessels would have lost contact with shore stations. Emergency services that rely on HF radio as a backup would have found that backup temporarily unavailable. For 30 minutes, a slice of modern infrastructure simply did not work, and there was nothing anyone could do about it except wait for the ionosphere to settle back to normal. Now scale that up. An X1.9 is a moderate X-class flare. The strongest flare of 2025 so far was the X516 that erupted on November 11th. That event caused R3 blackouts across Africa and Europe. The strongest flare of solar cycle 25 to date was an X9 on October 3rd, 2024, and the historical record contains events that dwarf even these. The flare associated with the Carrington Event is estimated to have been somewhere around X40 to X45. Some researchers place it even higher. That is not 10 times stronger than what hit Australia. It is not even 100 times stronger. Depending on the estimate, the Carrington flare may have been 400 to 1,000 times more powerful than the X1.9 that caused continent-wide radio blackouts on December 1st. Imagine what an X40 flare would do to modern communications. Not just high-frequency radio, but GPS signals passing through a suddenly chaotic ionosphere. Not just aviation and maritime, but emergency services banking systems that rely on precise timing power, grid synchronization that depends on GPS clocks. The alpha level on the NOAA scale extreme radio blackout describes complete high-frequency radio blackout on the entire sunlit side of Earth, lasting for several hours. Low-frequency navigation signals would be degraded for hours. Satellite navigation would experience errors on the sunlit side. That is not science fiction. That is the predicted consequence of a Carrington-class flare. And the Sun has produced such flares before. It will produce them again. The only questions are when and whether Earth will be in the firing line. The December 1st event was a reminder that the Sun is active, engaged and capable of reaching across the void to touch our technology. It was also a reminder that we have built a civilization increasingly dependent on systems that the Sun can disrupt with a single, well-aimed explosion. The radio blackout over Australia lasted 30 minutes and caused no lasting harm, but it was a small event from a small sunspot while the giant was still coming into view. The next few days will reveal whether AR4294 is content to rotate quietly across the solar disk, or whether it intends to make its presence known in ways that make an X1.9 look like a firecracker compared to a bomb. The historical record suggests we should not be complacent. The Sun has spoken before in languages far more forceful than what Australia heard on December the 1st. In 1859, it spoke loudly enough to set telegraph offices on fire. In 1989, it spoke loudly enough to collapse an entire power grid. And the tree rings, those ancient archives of cosmic radiation, whisper of events that make even the Carrington storm look modest. The sun has a voice and sometimes it screams, December's ticking time bomb. There is a window, a specific period of days when the danger reaches its peak, when the geometry of sun and earth aligns in the worst possible configuration. For AR4294, that window opens around December 4th and does not close until approximately December 7th. During those days, the massive sunspot complex will transit the central meridian of the solar disk, the region where any eruption, any coronal mass ejection, any violent release of magnetic energy will be aimed directly at our planet. Before and after that window, the risk diminishes. Flares still occur, ejections still happen. But they miss us sailing off into the cosmic void at angles that spare Earth from the full brunt of their fury. During the window, there is no margin for error. Whatever the sun releases will be coming straight for us. NOAA's Space Weather Prediction Center has already issued their forecast for the first week of December. They anticipate a 70% chance of M-class flares and a continued possibility of X-class events through December 5th. A coronal whole high-speed stream is expected to arrive around December 3rd, potentially elevating geomagnetic activity to G1 minor storm levels. This recurrent feature, a region where the sun's magnetic field opens outward and allows the solar wind to stream freely into space at elevated speeds, has been a regular visitor to Earth's environment. In early November, the same coronal hole produced strong to very strong solar wind conditions. Now it returns, adding another variable to an already complex situation. The forecast speaks in probabilities and technical classifications, the careful language of scientists who understand that predictions are not certainties. But beneath the measured tones lies genuine concern. AR4294 is not behaving like an ordinary active region. Its sheer size, its magnetic complexity, and its timing at the peak of an unexpectedly strong solar maximum combine to create a scenario that demands vigilance. Amateur astronomers around the world have been imaging the sunspots, sharing their observations on social media and astronomy forums. Victor Rogus, observing from Sedona, Arizona, captured the region while it was still emerging over the southeastern limb and noted that it appeared potentially dangerous. Valérie Lear in France described the complex magnetic structure with bright plonge areas and absorbing filaments that follow the magnetic field lines. These are not sensational claims. These are observations from experienced solar observers who recognize when something unusual is happening. The delta configuration remains the critical factor in solar magnetism. The arrangement of polarities determines stability. Imagine two bar magnets placed near each other. If their opposite poles face each other north to south, they attract and settle into a stable configuration. If their same poles face each other north to north or south to south, they repel and create tension. Now imagine those magnets embedded in a churning sea of plasma, their field lines twisted and tangled by convective motions deep beneath the visible surface. The energy stored in those twisted fields is immense, and it will eventually be released. The question is whether the release will be gradual through a series of small flares and slow reconnection events, or sudden through a catastrophic eruption that dumps all that stored energy into space at once. Delta sunspots favour the sudden option. The statistics are clear. Regions with delta magnetic configurations produce more than 80% of all major flares. They are the troublemakers of the solar surface, the active regions most likely to generate the X-class events that disrupt our technology and occasionally threaten our infrastructure. AR4294 has a delta configuration. It has already demonstrated its capability through the smaller flares that have crackled from its vicinity since it came into view, and it is growing. As more of the region rotates onto the visible disk, additional complexity is being revealed. NOAA has had to split the designation into multiple numbered regions simply to categorize what they are observing. This is not a single sunspot. It is a sprawling complex of magnetic activity that dominates the northeastern quadrant of the Sun. Consider what we know about the current state of solar cycle 25. This was supposed to be a quiet cycle, a continuation of the trend toward weaker activity that characterized cycle 24. The official predictions in 2019 called for a maximum of around 115 sunspots, reached sometime in July of 2025. Instead, activity has consistently exceeded forecasts. The cycle ramped up faster than expected. Sunspot counts reached levels not seen since the early 2000s. In October of 2024, the Solar Cycle Prediction Panel finally acknowledged what had become obvious to observers. Solar maximum had arrived, possibly as much as 2 years earlier than initially predicted, and it was proving stronger than the conservative estimates had suggested. This matters because solar maximum is when the most dangerous events occur, not exclusively, of course. Large flares can happen at any point in the cycle, but the probability peaks during maximum, when the sun's magnetic field is most complex and active, regions are most numerous. We are currently in that peak. The sun is at its most volatile, its most unpredictable, its most capable of producing the kind of event that could genuinely disrupt modern civilization. And into this period of elevated risk comes the largest sunspot in a decade, rotating toward the most geo-effective position on the solar disk. The next 72 hours represent a critical watch period, not because an eruption is certain, but because the conditions for a major event are present in a way they rarely are. Size alone does not guarantee activity. Some large sunspot groups rotate across the solar disk without producing significant flares. They are magnetically stable, the energy gradually dissipating through small-scale reconnection events rather than explosive releases. But the delta configuration argues against stability. The multiple X-class flares from the surrounding region argue against stability. The overall behavior of Solar Cycle 25 argues against expecting quiet outcomes. Space weather forecasters operate in a realm of uncertainty that would make meteorologists nervous. Weather prediction on Earth benefits from dense networks of sensors, decades of calibrated models and physical processes that, while complex, are relatively well understood. Space weather prediction relies on a handful of satellites models that are still being refined and a source of energy, the sun, that regularly defies expectations. The forecasters can tell you that conditions favour flare activity. They can estimate probabilities, but they cannot tell you with certainty whether AR4294 will produce an X10 flare tomorrow, or quietly decay over the next week without incident. The sun keeps its own counsel. What they can do is prepare. Power grid operators have been alerted to the elevated risk. Satellite operators have been notified. Airlines that fly polar routes where communications are most vulnerable and radiation exposure is highest have the information they need to make rerouting decisions. These preparations are routine during periods of elevated solar activity. They happen multiple times per year, usually without incident. The forecasters issue warnings, the operators take precautions, the event either occurs or does not occur, and life continues. This is the normal rhythm of space weather management, a quiet dance of preparedness that most of the public never sees. But there is a scenario that keeps space weather professionals awake at night. A scenario where the precautions are not enough, where the event exceeds the planning parameters, where the infrastructure designed to withstand certain levels of disturbance encounters something beyond its design limits. The Carrington event was such a scenario arriving before the infrastructure existed to be damaged. A Carrington-class event today would be something entirely different. We have spent 166 years building a technological civilization exquisitely sensitive to exactly the kind of disturbance that a major solar storm produces. We have done so without fully accounting for the risk, without hardening our critical systems, without preparing for an event that statistics suggest is not merely possible, but inevitable on a long enough timeline. The next few days may pass without incident. The giant sunspot may rotate harmlessly across the solar disk, producing spectacular images for amateur astronomers and causing nothing more than a few minor radio disturbances. This is the most likely outcome for any given active region. Most sunspots do not produce catastrophic flares. Most solar cycles do not include Carrington-class events. The base rate of major solar storms is low, which is why we have been able to build our technological society without constant disruption. But low probability is not zero probability. And when the consequences of an event are severe enough, even low probabilities demand attention. The financial industry understands this. They call them tail risks, the unlikely events at the far ends of the distribution that can nonetheless occur and cause catastrophic losses when they do. Space weather has its own tail risks, and AR4294 has put the world on notice that we are currently rolling the dice with a loaded coin. The Sun has produced Carrington-class events before. The ice cores tell us that. The tree rings tell us that. The historical records, sparse as they are, tell us that. And the Sun will produce such events again. The only uncertainty is timing, whether it happens this week, this year, this decade, or this century. The sunspot rotating into view does not guarantee that this is the moment, but it guarantees that the possibility is elevated that the conditions for a major event are present, and that the coming days demand more attention than usual from everyone who depends on the technology that solar storm could disrupt, which in the modern world is everyone. The Carrington warning we forgot. On the morning of September 1st, 1859, a 33-year-old English astronomer named Richard Carrington was doing what he did most clear days, projecting an image of the sun onto a white screen and carefully sketching the sunspots he observed. His observatory in Red Hill, Surrey was modest, but effective, equipped with a 412-inch telescope that allowed him to track solar features with considerable precision. Carrington had been observing the sun systematically for years, contributing to the growing scientific understanding of our nearest star. That morning he noticed a large group of sunspots in the Northern Hemisphere complex, an active, the kind of feature that demanded careful documentation. Then something happened that had never been recorded before. At 11:18 local time, two brilliant patches of white light appeared within the sunspot group, intensely bright against the already luminous solar surface. Carrington watched in astonishment as the lights moved across the face of the sunspot, travelling roughly 35,000 miles in 5 minutes before fading from view. He had witnessed a solar flare, the first ever observed by human eyes, though he did not know what to call it or what it meant. Rushing to find a witness, he was unable to locate anyone before the event ended. But unknown to Carrington, another astronomer, Richard Hodgson, was independently observing the same phenomenon from a different location in London. Their reports, published side by side in the monthly notices of the Royal Astronomical Society, would establish the first documented observation of a white light flare. What followed the flare was unprecedented in human experience. Approximately 1712 hours later, a massive geomagnetic storm struck Earth. This was extraordinarily fast. Coronal mass ejections typically take 2 to 4 days to traverse the distance between Sun and Earth. The Carrington CME arrived in under 18 hours, suggesting either extreme velocity or that a prior ejection had cleared the path of the solar wind, reducing the drag that normally slows such events. Whatever the cause, the impact was immediate and global. Telegraph systems across Europe and North America went haywire. Operators reported receiving severe electrical shocks from their equipment. Telegraph paper spontaneously caught fire in multiple offices. In some cases, the induced currents were so strong that operators could disconnect their batteries entirely and continue sending and receiving messages powered solely by the geomagnetically induced electricity flowing through the wires. The aurora borealis, normally confined to high latitudes, was visible as far south as the Caribbean, Colombia, and Hawaii. In the Rocky Mountains, gold miners woke at 100 in the morning thinking dawn had arrived, so bright was the auroral light. People across the world watched in wonder and fear as the sky burned red and green in colours they had never seen before. The Carrington Event, as it came to be known, was the largest geomagnetic storm in recorded history. Estimates of its intensity suggest it was roughly double the strength of the next most powerful measured event. The DST index, a measure of geomagnetic disturbance, is estimated to have reached between 800 and 1750 nanotesla. For comparison, the March 1989 storm that collapsed the Quebec power grid reached approximately 589 nanotesla. The Carrington event was 2 to 3 times stronger than the storm that blacked out an entire Canadian province. But in 1859 there was little to damage. The world ran on muscle power, steam power, and flame. The telegraph was the height of electrical technology, and even it was a novelty that most people had never used. There were no power grids to collapse, no satellites to disable, no GPS systems to scramble, no internet to go dark. The Carrington event was primarily a spectacle, a source of wonder, and some damaged equipment, but not a civilization-threatening catastrophe. The technological vulnerabilities that would make such an event genuinely dangerous simply did not exist. We have spent the intervening 166 years building exactly those vulnerabilities. The modern world runs on electricity in ways that would have been unimaginable to Carrington and his contemporaries. The power grid is not merely convenient, it is essential to every other system that sustains our civilization. Without electricity, water treatment plants stop operating. Pumping stations that move clean water to homes and businesses fall silent. Sewage systems that depend on powered lifts begin to back up. Hospitals lose the ability to run ventilators, dialysis machines, and refrigeration for medications. Gas stations cannot pump fuel. Grocery stores cannot refrigerate food or process transactions. Traffic signals go dark. Communication networks collapse as cell towers exhaust their backup batteries. Within hours of a major grid failure, the cascade of secondary effects begins to accumulate. Within days, it becomes a crisis. Within weeks, it threatens lives on a massive scale. A Carrington-class event today would not merely be inconvenient. Multiple studies have attempted to estimate the damage. Lloyd's of London, the insurance market that has been assessing risk for over 3 centuries, commissioned a report examining the potential cost of a Carrington-level storm striking the United States. Their estimates range from $600 billion to $2.6 trillion, depending on the severity and duration of the impacts. That was in 2013. Adjusted for inflation, the figures would be significantly higher today. More importantly, the estimates focus primarily on direct damage and immediate economic disruption. They did not fully account for the cascading failures that would result from extended power outages across multiple states or regions. The vulnerability lies primarily in the high-voltage transformers that form the backbone of the power grid. These massive devices, some weighing over 400 tons, step voltage up for efficient long-distance transmission and step it down for local distribution. They are expensive, custom-built, and require 12 to 18 months to manufacture under normal conditions. The United States has approximately 2,000 of these extra-high voltage transformers, and there is no significant domestic manufacturing capacity. Most are built overseas. There is no strategic reserve of spare transformers waiting to replace damaged units. A geomagnetic storm that destroyed or severely damaged even a fraction of these transformers could result in power outages lasting not days but months, or potentially years. The mechanism of damage is subtle but relentless. When a CME strikes Earth's magnetosphere, it induces electric currents in long conductors at the surface. Power lines act as antennas, gathering these geomagnetically induced currents, GICs, and channeling them into the grid. The currents flow through transformers seeking ground. But transformers are designed for alternating current at 50 or 60 Hz, not the quasi-direct current produced by geomagnetic disturbances. The induced currents cause the transformer cores to saturate, magnetically generating heat in places the equipment was never designed to handle. The insulation degrades, hotspots develop. In extreme cases, the windings can melt, the oil can catch fire, and the transformer can be destroyed. This is not theoretical. It happened in March 1989 in Quebec. A geomagnetic storm approximately 133, the intensity of the Carrington event, caused the Hydro-Quebec grid to collapse in 92 seconds. 6 million people lost power for up to 9 hours in the middle of a harsh Canadian winter. But this damage extended further. A transformer at the Salem nuclear plant in New Jersey was destroyed by the induced currents. Within 2 years of the storm, 11 nuclear plants reported failures of generator step-up transformers that were likely linked to the event. The storm was moderate by historical standards. It was not even close to Carrington-class. And yet it demonstrated exactly how vulnerable our infrastructure is to space weather. The European Space Agency conducted exercises in 2025 simulating what a Carrington-level event would mean for satellite operations and ground infrastructure. The results were sobering. They modelled atmospheric swelling of up to 400%, which would drag satellites out of their orbits. They simulated communication blackouts, GPS degradation, and the inability to track space debris. The exercise was not meant to reassure anyone. It was meant to demonstrate how unprepared we remain for an event that we know is possible, that we know has happened before, and that we know will happen again. Richard Carrington suspected a connection between the solar flare he observed and the geomagnetic storm that followed, but he was cautious, famously writing that one swallow does not make a summer. He could not be certain that correlation implied causation. Today we understand the physics completely. Solar flares release electromagnetic radiation that arrives at light speed, causing immediate ionospheric disturbances. Coronal mass ejections follow carrying magnetized plasma that interacts with Earth's magnetic field to produce geomagnetic storms. The connection is not speculative. It is measured, modelled and monitored continuously by satellites and ground-based instruments. What we have not done is act on that knowledge at a scale commensurate with the risk. The power grid remains largely unprotected. Spare transformer capacity remains inadequate. Warning systems can provide hours to days of notice for an incoming CME, but the preparations that can be made in that time frame are limited. Operators can reduce load. They can open certain circuits to prevent the induced currents from flowing through critical equipment, but they cannot harden a grid in hours that should have been hardened over decades. The Carrington event was a warning written in aurora fire across the sky of 1859. We marvelled at it. We documented it. And then we built a civilization that forgot the lesson it should have taught us. The sun has not changed. It still produces major storms. It still hurls billions of tons of magnetized plasma into space at thousands of kilometers per second. The only thing that has changed is us, and not in ways that make us more resilient. We have made ourselves more vulnerable with every wire we string, every satellite we launch, every system we build that depends on the continuous flow of electricity. The question is not whether another Carrington event will occur. It will. The question is whether we will be ready when it does. Right now the answer is almost certainly no. Whispers in the tree rings. In 2012, a physics graduate student at Nagoya University in Japan made a discovery that would rewrite our understanding of solar violence. Fusa Miyake was not looking for anything extraordinary. Her project involved a new highly sensitive technique for measuring carbon-14 in tree rings, a refinement of radiocarbon dating that allowed analysis of individual annual growth layers rather than average samples spanning decades. She travelled to a lush island in southern Japan, famous for its ancient cedar trees, some nearly 1900 years old. She cut a slice from an old stump counted back through the rings, and began measuring the radioactive carbon content year by year. What she found in the ring, corresponding to 774 to 775 AD, was impossible to ignore. The carbon-14 level spiked by approximately 12% compared to adjacent years. This was not a gradual increase or a measurement error. It was a sharp single-year jump roughly 20 times greater than the normal year-to-year variation caused by ordinary cosmic radiation. Something had happened in 774 or 735 that dramatically increased the production of carbon-14 in Earth's atmosphere. Something powerful, something brief, something that left its signature in the wood of trees around the world. Carbon-14 forms when high-energy particles from space collide with nitrogen atoms in the upper atmosphere, knocking out protons and converting the nitrogen into a radioactive isotope of carbon. This carbon-14 then combines with oxygen to form carbon dioxide, which circulates through the atmosphere and gets absorbed by living things. When a tree grows a new ring, it incorporates the carbon dioxide available that year, including whatever carbon-14 is present. When the tree stops growing when that ring is complete, The carbon-14 is locked in, slowly decaying over thousands of years at a known rate. By measuring how much remains, scientists can determine when the ring formed. But Miyake was not trying to date the tree. She was trying to measure cosmic ray intensity over time, and the spike in 774 told her that the cosmic ray flux had temporarily increased by an enormous amount. Other researchers quickly confirmed her finding. The same spike appeared in tree rings from Germany, Russia, the United States, Finland, and New Zealand. Whatever had caused the event, it was global. A matching surge in beryllium-10, another cosmogenic isotope, was found in Antarctic ice cores corresponding to the same period. The evidence was unambiguous. Earth had been bombarded by an intense burst of high-energy particles sometime around 774 or 775 AD, and the signature of that bombardment was preserved in trees and ice around the planet. The leading explanation was a solar storm. The Sun produces energetic particles during flares and coronal mass ejections, particles that can reach Earth and interact with the atmosphere in exactly the way needed to produce carbon-14 and beryllium-10. But the scale was troubling. The Carrington Event, the largest solar storm in recorded history, did not produce a detectable spike in the cosmogenic isotope record. It was too small. Whatever happened in 774 was at least 10 times more powerful than the Carrington Event, possibly much more. Some estimates suggested it was 80 times stronger. The Sun had apparently produced a storm of unprecedented violence, a storm that made Carrington look modest by comparison. These events are now called Miyake Events, named after the graduate student who first identified them. Since her initial discovery, researchers have found additional spikes in the tree ring record. Another occurred in 993 to 994 AD, about 60% as strong as the 774 event. Others have been identified around 660 BC, 52-509 BC, 519 BC, and 7176 BC. The most powerful event yet discovered occurred approximately 14,300 years ago, preserved in ancient trees recovered from eroded riverbanks in the French Alps. That event was roughly twice as strong as the 774 spike, which itself was already an order of magnitude beyond anything in the historical record. The implications are staggering. These events are not hypothetical. They happened. The evidence is written in ancient wood and ancient ice, archives that have no reason to lie and no capacity for exaggeration. The Sun has produced storms of extraordinary power multiple times during the Holocene, the geological epoch, encompassing all of human civilization. These storms did not end the world. Life continued. Civilizations rose and fell for reasons unrelated to solar activity. But these storms occurred before we built a technological infrastructure that depends on the very systems most vulnerable to solar bombardment. Imagine a Miyake event occurring today. Not a Carrington event, not the storm we usually cite as the worst-case scenario, but something 80 times more powerful. The Carrington event would collapse power grids and damage transformers. A Miyake event would do something far worse. The radiation dose at aircraft altitudes would be dangerous, possibly lethal for passengers on polar flights. Satellites would be bombarded with particles that could fry their electronics instantly. Not through the slow accumulation of charge, but through direct damage to circuits and components. The ionospheric disturbance would be so severe that GPS might be unusable for days, not hours. Power grids would face induced currents beyond anything they were designed to withstand. The cascading failures would be faster, deeper, and more difficult to recover from than any scenario currently modelled by emergency planners. The historical record offers a few tantalising hints about what people experienced during these events. The Anglo-Saxon Chronicle, a collection of annals recounting English history, contains an entry for 774 that describes a red crucifix seen in the sky after sunset. This is consistent with a powerful aurora visible at unusually low latitudes. Chinese records from the same period mention abnormal celestial phenomena, but the documentation is sparse. These societies had no framework for understanding what they were witnessing, and their records focused on interpretation rather than description. A red cross in the sky was a sign from God, not a plasma phenomenon to be measured and analysed. What we can say with confidence is that Miyake events are real, that they occur with some regularity over millennial timescales, and that they represent a category of solar violence far beyond anything in the historical record. The rough frequency appears to be approximately 1 event per 1,000 years, though the statistics are uncertain given the limited number of confirmed examples. 1,000 years is a long time by human standards, but a blink in geological terms. The last confirmed Miyake event occurred in 993 or 994 AD, slightly over 1,000 years ago. We are statistically within the window where another could occur. There is a debate among scientists about whether these events are even produced by the sun. The energy required is extreme beyond what standard models of solar flares can easily explain. Some researchers have proposed alternative explanations, including supernovas or gamma-ray bursts from distant sources, but the evidence tilts toward a solar origin. The isotope ratios match what would be expected from solar energetic particles. The events appear to have durations measured in years, rather than the brief pulses expected from extrasolar sources, and the sun is demonstrably capable of extreme behaviour. We simply may not have observed the full range of what it can do. This uncertainty is itself unsettling. We do not fully understand the mechanism that produces Miyake events. We cannot predict when the next one will occur. We have only recently recognised that such events exist at all, thanks to Fusa Miyake's careful work with tree rings just over a decade ago. Our ignorance is profound, and yet we have built a civilization that would be devastated by such an event. A civilization whose survival in its current form may depend on the sun continuing to behave within bounds we have only recently discovered it can exceed. The tree rings whisper warnings across millennia. They tell us that the Carrington event, as terrifying as it sounds, is not the worst case. They tell us that the sun has reached out with far more violence than anything in our written history. They tell us that we are gambling with forces we barely understand, betting that the extreme events will not happen on our watch, that the statistical rarity will protect us long enough to figure out how to prepare. It is a reasonable bet. Perhaps Miyake events are rare. The odds that one occurs in any given year are low, but the odds are not zero, and the consequences of being wrong are severe. The ancient cedars of Japan have been keeping records for nearly 2,000 years. They recorded the 774 event and the 994 event without understanding what they were documenting. They continue to grow today, adding rings year by year, archiving the cosmic ray flux for future scientists to analyse. Somewhere in the outermost rings, the signature of the current solar cycle is being written. Future researchers will be able to look back at 2025 and see how active the sun was, how many cosmic rays bombarded the atmosphere, whether anything unusual happened during the month when the largest sunspot in a decade rotated into view. We cannot predict what those future researchers will find. We can only watch and wait and hope that the sun remains within the bounds of what our civilization can survive. The tree rings suggest those bounds are wider than we assumed, that the sun is capable of violence we have never directly witnessed. Whether it chooses to demonstrate that capability while we are watching is a question only time will answer. Time will. The first 48 hours of darkness. Let us imagine it happens. Not hypothetically, not as an abstract possibility to be considered and dismissed, but concretely, specifically, with all the mundane, terrifying details that would define the experience for ordinary people. A massive coronal mass ejection erupts from a sunspot complex aimed directly at Earth. The forecasters detect it immediately. Coronagraph images show a full halo expanding outward from the sun, indicating the material is headed straight for us. Velocity measurements confirm the worst. This is a fast CME travelling at over 2,000 km/s. Impact is expected in less than 18 hours. Warning messages go out to power grid operators, satellite companies, airlines, and government agencies. The public is told to prepare for potential disruptions. Most people hear the news shrug and continue with their days. Geomagnetic storms happen. The lights flickered a bit back in May. Nothing to worry about. The CME arrives ahead of schedule, slamming into Earth's magnetosphere in the early morning hours. The magnetic field orientation is the worst possible, southward pointing, which allows the solar material to couple efficiently with Earth's magnetic field. The magnetosphere compresses violently. Geomagnetically induced currents begin flowing through long conductors at the surface power lines, pipelines, communication cables. Within minutes, the first transformers begin to overheat. Grid operators, many of whom were already implementing protective measures, watch their systems destabilize faster than they can respond. Circuit breakers trip. Load balancing fails in several regions simultaneously. Voltage collapse cascades through interconnected networks. The lights go out. The first hour is confusion. In densely populated areas, the outage seems like any other blackout, annoying but temporary. People reach for their phones to check social media to find out what happened, to see how long before power returns. Cell service is spotty. The towers have backup batteries, but the network is congested with everyone trying to connect at once. News websites load slowly or not at all. Those who manage to get information learn that this is not a local outage. It is regional. It may be national. The scope is still unclear. By the second hour, traffic has become chaotic. Every intersection without power is a four-way stop, but many drivers do not treat them that way. Accidents snarl major routes. Emergency services are responding to multiple incidents simultaneously, their communications hampered by overloaded and partially degraded networks. Hospitals have switched to backup generators, but some are discovering that the geomagnetic storm has damaged sensitive equipment. Diagnostic machines give erratic readings. Monitoring systems glitch. Staff improvise, falling back on older methods, paper charts, manual measurements. By the fourth hour, the sun has risen on a changed landscape. In unaffected regions, life continues more or less normally, but those areas are fewer than expected. The geographic footprint of the damage is becoming clear. Multiple states have lost power entirely. Others have partial service, with utilities scrambling to isolate damaged sections and restore what they can. The stock markets do not open. Financial systems that depend on precise timing synchronization are experiencing failures. GPS satellites are still transmitting, but the signals are degraded, and ground-based systems that rely on GPS for timing are misbehaving. Trucking companies are having difficulty tracking their fleets. Airlines have grounded flights partly due to communication issues and partly due to uncertainty about navigation systems. For people in the affected areas, the fourth hour brings the first real inconveniences. Refrigerators have been off long enough that food is beginning to warm. Those with gas stoves can still cook, but electric stoves and microwaves are useless. Water still flows from taps because elevated storage tanks maintain pressure through gravity, but the pumps that would refill those tanks are not running. No one worries about water yet. The outage is only a few hours old. Surely power will return soon. By the 12th hour, the mood has shifted. This is no longer a minor disruption. Cell phone batteries are dying and there is no way to recharge them. Information becomes scarce and unreliable. Rumors spread. Some say the entire country is dark. Others say power will be restored by evening. No one knows for certain because the normal channels of communication are compromised. People begin to realize how dependent they are on electricity for things they never consciously thought about. The internet is largely inaccessible. Television is obviously unavailable. Even battery-powered radios struggle to find stations that are still broadcasting. The first night is long. Cities that normally glow with light are dark, revealing stars that urban residents have never seen. The novelty wears off quickly. Without heating in cold climates or cooling in hot ones, homes become uncomfortable. People layer clothing or open windows, making do with what they have. Most assume this will be over tomorrow. Major infrastructure failures do not happen in modern countries. This is temporary. By the 24th hour, water pressure begins to drop in some areas. The elevated tanks are depleting and the pumps remain offline. People who turn on their taps find only a trickle, then nothing. This is when anxiety starts to build. Water is not optional. You can go days without electricity, uncomfortable but survivable. You cannot go long without water. grocery stores, the few that opened with cash-only transactions and manual record-keeping, begin to see runs on bottled water. Supplies that seemed adequate for normal demand disappear within hours. The 36th hour brings the first real shortages. Gas stations cannot pump fuel without electricity. Even those with generators are running low on diesel. Trucks that would normally resupply stores are stuck, unable to refuel, unable to navigate efficiently without GPS-facing roads, clogged with vehicles that have run out of gas. The supply chain, that invisible network that keeps modern society fed and functioning, begins to stutter. Perishable food in warehouses is spoiling. Refrigerated trucks are becoming expensive metal boxes. The carefully orchestrated logistics of just-in-time delivery, the system that ensures grocery shelves are restocked daily, falls apart when any link in the chain breaks. By the 48th hour, the contours of the crisis are clear. This is not a brief outage that will be resolved with a few repairs. Transformers have been destroyed, not tripped offline but physically damaged. Their windings burned, their oil contaminated, their cores saturated beyond recovery. Replacing them will take months under the best circumstances. Some cannot be replaced at all without manufacturing new units, a process that requires 18 to 24 months in normal times, and longer when demand suddenly spikes. The utilities are performing triage, trying to restore power to the most critical facilities, first hospitals, water treatment plants, emergency services. But there is not enough generating capacity that survived the storm, and the transmission lines needed to deliver power are themselves damaged in places. 48 hours without electricity is survivable for most people. It is uncomfortable, inconvenient, and frightening, but it is not fatal. The danger lies in what happens next. If power is restored within a week, society can recover. People will have stories to tell. Businesses will count their losses and life will resume. If power remains out for weeks or months, the calculation changes entirely. Food runs out. Water becomes critical. Medical conditions that depend on electricity for management become life-threatening. The social fabric, already strained, begins to fray. This scenario is not fantasy. It is the explicit warning contained in multiple government and industry studies. The Federal Energy Regulatory Commission has identified 30 critical high-voltage transformers whose loss could cause cascading failure across the grid. Some analyses suggest that the simultaneous loss of as few as 9 key transformers in the wrong combination could result in a coast-to-coast blackout. The recovery time for such an event would not be measured in days. It would be measured in months or years, depending on the availability of replacement equipment and the extent of secondary damage caused by the outage itself. In the first 48 hours, most people would not yet understand the scale of what had happened. They would be waiting for normal to return, rationing their phone batteries, eating food from their pantries, trusting that the systems they depend on would come back online. The realization that normal might not return for a very long time would come later. In the third day, the fourth day, the first week without power, when the supplies run out and the help fails to arrive, that realization would transform an inconvenience into a catastrophe and test the resilience of individuals, communities, and nations in ways that have not been tested since the development of the modern power grid. All of this begins with a single event, a storm from the sun, a burst of magnetized plasma that we can see coming but cannot stop. The warning time might be 18 hours, it might be less. The preparations that can be made in that window are limited. And when the storm arrives, when the geomagnetically induced currents begin to flow, the outcome depends entirely on decisions made years or decades before. On whether the grid was hardened, on whether spare transformers were stockpiled, on whether the infrastructure was designed to withstand what the sun can deliver. 48 hours is just the beginning. When water stops flowing, there is a hierarchy of needs that becomes brutally clear when the systems we take for granted fail. Electricity is the foundation, the invisible substrate on which everything else depends. But electricity itself is not what keeps us alive. Water is. Clean potable water delivered to our homes through pressurized pipes treated and disinfected to remove pathogens available in unlimited quantities at the turn of a handle. We drink it. We cook with it. We bathe in it. We flush our waste with it. The average American uses between 80 and 100 gallons per day. Most of it without conscious thought. And almost all of it depends on electricity. Water treatment plants run continuously processing raw water through filtration, sedimentation, and chemical treatment before pumping it into the distribution system. The pumps that move water from reservoirs to treatment facilities are powered. The pumps that move treated water into elevated storage tanks are powered. The sensors that monitor water quality, the systems that inject precisely measured amounts of chlorine, the computers that control valve operations and track pressure throughout the network, all of it runs on electricity. Take away the power and the entire system begins to fail. Most municipalities maintain some reserve capacity. Elevated tanks and water towers use gravity to maintain pressure in the distribution system even when pumps are offline. Texas regulations, for example, require large cities to store at least 200 gallons per connection, with half of that in elevated or pressurized storage that will continue to flow without power. Other states have similar requirements. These reserves provide a buffer typically lasting somewhere between several hours and a couple of days, depending on the size of the system and the rate of consumption. But buffers are not solutions. They are delays. Every gallon that flows from the tap during a power outage is a gallon that is not being replaced. When the elevated tanks run dry, pressure drops. Taps begin to sputter and fail. Within 2 to 3 days of a major grid failure, most urban areas would exhaust their gravity-fed reserves. From that point forward, no water flows without power to the pumps. The consequences cascade. Hospitals depend on water for everything from sterilization to cooling medical equipment to basic sanitation. Even those operating on backup generators will face a crisis when their water supply fails. Firefighting becomes difficult or impossible in areas with depleted pressure. A house fire that would normally be contained becomes a conflagration because hydrants produce only a trickle. Sanitation systems that rely on water to carry waste away from homes begin to fail. Toilets back up. The smell becomes unbearable within days. People resort to disposing of waste in yards, in alleys, in any available space. The risk of disease transmission rises dramatically. In developing countries where infrastructure is less robust, we have seen what happens when water systems fail. Outbreaks of cholera, typhoid, and dysentery follow predictably. In a modern developed nation, the pathogens are less prevalent to begin with, but the conditions that allow them to spread would be created rapidly contaminated water sources, inadequate sanitation, crowded conditions as people cluster around locations with access to resources. The public health infrastructure that normally contains outbreaks would itself be compromised. Hospitals, overwhelmed laboratories unable to process samples, communication systems degraded. The psychological impact of losing water access should not be underestimated. People can tolerate darkness. They can tolerate cold or heat for a time. They can tolerate inconvenience and uncertainty. But the sudden unavailability of water triggers a primal response. Water is life. Without it, survival is measured in days, not weeks. When taps run dry, the veneer of civilization cracks quickly. People who would never consider stealing under normal circumstances will take whatever they need to keep their families hydrated. The social contract that depends on everyone having their basic needs met comes under severe strain. Consider the logistics of emergency water distribution. In a localized disaster, a hurricane or earthquake affecting a single city or region outside resources can be mobilized to bring in bottled water and tanker trucks. But a nationwide grid failure affects everywhere simultaneously. There is no unaffected region to provide aid. National Guard units that would normally deploy to disaster zones are dealing with crisis in their own states. Federal resources are spread impossibly thin. The scale of need vastly exceeds the capacity to respond. A single person needs roughly 1 gallon of water per day for drinking and minimal hygiene. A family of 4 needs 4 gallons. A city of 1 million people needs 1 million gallons daily just for drinking, not counting sanitation, medical facilities, or any other use. That is approximately 3,800 tons of water per day for drinking alone. Delivering that by truck when fuel is scarce and roads are clogged is a logistical nightmare. Delivering it to 330 million people simultaneously is simply impossible. Natural water sources become critical. Rivers, lakes, streams, wells. In rural areas with access to groundwater, those with manual pumps or the ability to improvise them will manage. In suburban and urban areas, the situation is far more difficult. Surface water is not safe to drink without treatment. It contains bacteria parasites and potentially chemical contaminants that can cause serious illness or death. People who drink from rivers and ponds in desperation will get sick. Some will die. The knowledge of how to purify water through boiling filtration or chemical treatment is not universally distributed. Many people have never considered the question and would not know where to begin. Boiling requires fuel. In a prolonged power outage, fuel becomes scarce. Natural gas pipelines may continue to operate for a time, but many homes use electricity for cooking. Wood can be gathered and burned, but in urban areas wood is not readily available. The practical challenges of purifying enough water to sustain life become overwhelming for people who have never had to think about where their water comes from. The timeline is unforgiving. A healthy adult can survive perhaps 3 to 5 days without water depending on conditions. Children and the elderly are more vulnerable. Those with medical conditions requiring hydration are at immediate risk. By the 4th or 5th day of a major grid failure, if water supplies have not been restored or alternative sources secured, the death toll begins to climb. Not from violence, not from disease, not yet, but from simple dehydration, the most basic failure of biological needs. This is why water infrastructure is considered critical in emergency planning. This is why utilities prioritize water treatment plants when allocating emergency power. This is why the loss of the grid is not merely an inconvenience, but an existential threat. The technology that delivers clean water to hundreds of millions of people depends entirely on the continuous availability of electricity. Remove that electricity for long enough and the consequences are not speculative. They are biological certainties. In the 1989 Quebec blackout power was restored within 9 hours. Water systems never fully depleted. In the 2003 Northeast blackout, the largest in North American history power, was restored to most areas within 2 days. Again, water systems remained functional throughout. We have not experienced a prolonged widespread grid failure in the modern era. We have not tested the limits of our reserves. We have not discovered what happens when millions of people simultaneously face dehydration. The studies that model these scenarios consistently reach the same conclusions. Extended grid failure results in mass casualties primarily from the failure of water and sanitation systems. The Congressional EMP Commission estimated that a prolonged nationwide blackout could result in the death of 3 to 90% of the American population within a year. That estimate is disputed, considered by some to be alarmist, but even the more conservative analyses acknowledge that mortality would be significant, numbered in hundreds of thousands, at minimum potentially millions depending on duration and scope. The sun does not intend malice. It is a ball of plasma undergoing nuclear fusion indifferent to the civilizations that orbit it. When it produces a massive ejection, it is not targeting Earth. It is simply doing what stars do. But the consequences of that indifferent violence fall on beings who have built their survival around assumptions that the sun invalidates. We have assumed that electricity will always be available. We have assumed that clean water will always flow from our taps. We have built cities of millions of people in locations that cannot sustain human life without continuous technological intervention. Those assumptions may be correct most of the time. The grid is resilient. Water systems are engineered with redundancy. Emergency plans exist. But the Carrington Event happened. Miyake Events happened. The sun has demonstrated capabilities that exceed our planning parameters, and when water stops flowing, the countdown begins. 3 days 5 at most. After that, the survivors are those who found alternatives, and the rest become statistics in a disaster that could have been prevented with sufficient preparation. The question is not whether water systems can fail. We know they can. The question is whether we have done enough to ensure they do not, or whether we are trusting luck to protect us from a threat we understand, but have chosen not to adequately address. The Great Unraveling. Modern civilization is a machine of staggering complexity. Billions of interlocking parts moving in coordination across continents and oceans. We do not see the machine because we live inside it. The food on grocery shelves appears as if by magic restocked overnight from sources we never consider. The gasoline in our tanks flows from refineries connected to pipelines, connected to tankers, connected to oil fields on the other side of the world. The medications in our cabinets were manufactured in facilities we have never heard of using raw materials sourced globally, distributed through networks that span nations. None of this coordination happens by accident. It happens because of electricity, because of communications, because of computers tracking inventory and routing shipments and processing payments billions of times per day. Remove the electricity and the machine stops. Not gracefully, not with an orderly shutdown, but violently, catastrophically, with components failing in cascades that ripple outward from the initial disruption. The supply chain that feeds and clothes and houses modern populations is not resilient. It is optimized. Every redundancy has been eliminated in the name of efficiency. Warehouses hold minimal inventory because sophisticated logistics can deliver new stock within hours. Manufacturers rely on just-in-time delivery because maintaining large stockpiles ties up capital. The entire system runs on the assumption that nothing will interrupt the continuous flow of goods from origin to destination. A prolonged grid failure interrupts everything simultaneously. Within days, grocery stores are stripped bare not because the food does not exist, but because it cannot be delivered. Trucks need fuel, and fuel stations need electricity to pump. Drivers need to know where to go, and GPS systems are degraded or unavailable. Warehouses need to process orders, and their computers are dark. Payment systems are offline. The intricate dance of supply and demand grinds to a halt, not because any single component has failed, but because every component depends on every other component and they have all failed together. Fuel is the critical bottleneck. Without fuel, nothing moves. The trucks that deliver food, the trains that carry grain, the ships that transport goods across oceans, all depend on continuous access to refined petroleum products. Refineries require electricity to operate. Pipelines require electricity to pump. Storage facilities require electricity for safety monitoring. The Strategic Petroleum Reserve exists to buffer temporary disruptions, but it was never designed for a scenario where the entire distribution infrastructure is offline. Oil in a tank is useless if you cannot move it to where it is needed. The domino effect is relentless. Without fuel generators that are providing backup power to critical facilities run dry. Hospitals that were managing on emergency power go dark. Cell towers that were maintaining partial service with battery backups finally fall silent. The last connections to the outside world disappear. Communities that had been hoping for rescue realize that no rescue is coming, that the rest of the country is facing the same crisis, that they are on their own. Food becomes the currency of survival. The average American household keeps approximately 3 to 5 days of food on hand. In an extended emergency, that supply disappears quickly. Community food banks and emergency shelters are overwhelmed within the first week. Government supplies, the 6 million emergency meals stockpiled by FEMA, would not feed the country for a single day, even if they could be distributed effectively. In a nationwide grid failure, they cannot be. The logistics of emergency response depend on the same infrastructure that has failed. The military, which many assume would step in to restore order, is itself dependent on the civilian grid for 99% of its domestic power needs. Social order begins to fray at the edges. In the first days, people cooperate. They share resources, check on neighbours, wait patiently for instructions from authorities. But as days become weeks, as hunger sets in, as the realization dawns that the crisis may last months rather than days, cooperation gives way to desperation. Those with supplies become targets for those without. Violence that would have been unthinkable under normal circumstances becomes rational when the alternative is watching your children starve. History provides precedents, none of them reassuring. Societies that have experienced extended breakdowns of central authority, whether through war, natural disaster, or economic collapse, follow recognizable patterns. Initial cooperation gives way to factional competition. Those with weapons and organization gain power. Those without become dependent or victimized. The speed of this transition depends on cultural factors, on the severity of the shortage, on the perceived likelihood of recovery. In a scenario where recovery appears distant or uncertain, the transition can be rapid. We do not like to imagine this. It conflicts with our self-image as a civilized people governed by laws and norms that constrain behavior even in difficult times. But the laws and norms depend on enforcement, on the expectation that violators will be caught and punished. When police departments cannot communicate when courts are closed, when jails are unable to hold prisoners because they cannot provide water and food, the enforcement mechanism dissolves. What remains is informal social control, the influence of community and family and personal ethics. For many people, this would be enough. For some, it would not. The economic impact extends beyond the immediate crisis. Stock markets around the world would crash, assuming they were able to open at all. The interconnected nature of global finance means that a collapse in one major economy cascades instantly to others. Foreign factories that depend on American consumers would shutter. International shipping that relies on American ports would reroute or cease. The dollar, already under pressure in various scenarios, might face questions about its status as the global reserve currency. The recovery, when it comes, would be starting from a far lower baseline than the moment before the storm. Insurance companies have modelled these scenarios. Lloyd's of London estimated $2 to $3 trillion in damage from a Carrington-class event, but that estimate assumes a functioning society capable of rebuilding. It assumes that insurance companies themselves remain solvent, that contracts can be enforced, that the economic system survives to process claims. In a severe enough scenario, insurance becomes meaningless because the concept of monetary value itself becomes unstable. The populations most at risk are those most dependent on technology urban areas with high population density and limited local resources. Communities that have built around the assumption of continuous imports of food, water and energy. Individuals who depend on daily medication, refrigerated insulin, dialysis, powered medical devices. The elderly, the disabled, the very young. Anyone whose survival margin is already narrow. A prolonged grid failure would not kill everyone. It would kill those least able to adapt to conditions their bodies and circumstances cannot tolerate. We have not experienced this in the developed world within living memory. The closest analogies are partial and local. Puerto Rico, after Hurricane Maria, spent months without power, and the death toll initially reported in the dozens was eventually revised to nearly 3,000. The Texas freeze of 2021 killed over 200 people in less than a week, in an event that affected only a single state, and was resolved relatively quickly. These events hint at what a nationwide months-long grid failure might produce, but they are pale shadows of the full scenario. The historians of the future, if there are historians and if they have access to records of this period, would note that we knew. We had reports from congressional commissions, we had studies from insurance companies, we had the explicit warnings of scientists who understood the threat, and we chose collectively not to act at a scale commensurate with the risk. We chose to optimize for efficiency rather than resilience. We chose to trust that the rare event would remain rare long enough for it to become someone else's problem. The sun does not care about our choices. It produces coronal mass ejections according to the physics of magnetohydrodynamics, not according to our preferences or preparations. When the next major storm arrives, whether it is the current sunspot or one decades from now, it will find whatever society we have built waiting, prepared or unprepared, resilient or fragile, capable of absorbing the blow and recovering or not. The great unraveling is not inevitable. It is a choice, the accumulated consequence of millions of smaller choices about investment preparation and risk tolerance. But if it comes, it will come quickly. The machine of modern civilization is not designed for graceful degradation. It is designed to run at full speed, and when it stops hard. Civilizations that vanished before us, We tend to think of our civilization as permanent as the inevitable culmination of human progress, as something that will continue indefinitely into the future with only improvements and refinements. This is a failure of imagination. History is littered with the ruins of societies that believe themselves equally permanent, equally inevitable, equally destined to endure. The Maya built cities of hundreds of thousands of people, developed sophisticated mathematics, and astronomy, created a written language and monumental architecture. Their descendants still live in Central America, but the civilization that built Tikal and Chichen Itza collapsed between 800 and 1000 AD. The population declined by 90% or more. The great cities were abandoned to the jungle. The complex society that had thrived for over a millennium simply ended. The collapse of Maya civilization took decades, perhaps centuries, to fully play out. Scholars still debate the exact causes, some combination of drought, warfare, deforestation, and political fragmentation. But the underlying dynamic is clear. The Maya built a society that exceeded the carrying capacity of its environment under stress conditions. When those stress conditions arrived, the systems that sustained dense populations failed. Without the systems, the populations could not be sustained. People died or migrated, cities emptied, knowledge was lost. The Bronze Age collapse around 1200 BC was even more dramatic. In a span of roughly 50 years, virtually every major civilization in the eastern Mediterranean failed. The Hittite Empire, which had dominated Anatolia for centuries, vanished. The Mycenaean kingdoms of Greece fell into a dark age from which they would not emerge for 400 years. Egypt survived barely but was permanently weakened. The Sea Peoples, whoever they were, swept through the region, leaving destruction in their wake. But the Sea Peoples were likely as much symptom as cause. Something had destabilized the entire interconnected system of Bronze Age trade and diplomacy. Drought earthquakes, plague, internal rebellion. All have been proposed. The truth is probably that multiple factors converged, each one making the others worse, until the cascading failures became self-sustaining. What links these collapses and what makes them relevant to our current moment is complexity. Complex societies are more productive than simple ones. They can support larger populations, create more sophisticated technologies, generate more wealth. But complexity comes with costs. It requires energy to maintain. It creates interdependencies that are efficient when things work, but catastrophic when they fail. It concentrates knowledge and capability in specialized institutions that cannot be easily replicated if they are lost. The Maya built water management systems that allowed agriculture in regions that could not support it naturally. When those systems failed, the regions could not support the populations that depended on them. Our civilization is the most complex in human history. The Bronze Age trade networks that connected Egypt to Mesopotamia to the Aegean seem primitive compared to the global supply chains that connect every corner of the modern world. The Maya water management systems were sophisticated for their time, but would be considered basic infrastructure today. We have built a civilization of astonishing capability, one that can split atoms, reach other planets, and communicate instantly across the globe. We have also built a civilization of astonishing fragility, one that depends absolutely on continuous flows of energy and information that can be interrupted by a single well-aimed storm from our own star. The Norse Greenland colony offers another cautionary tale. Vikings settled Greenland around 1000 AD, establishing a European agricultural society in one of the most hostile environments on Earth. For nearly 500 years they persisted. They built churches, raised cattle, traded with Europe. Then they vanished. The last written record dates from the early 1400s. When European ships returned in the 15th century, they found ruins and no living inhabitants. The Norse had failed to adapt to changing conditions. They had insisted on maintaining European practices, cattle farming and grain cultivation, in an environment increasingly unsuited to them. Meanwhile, the Inuit who had arrived in Greenland around the same time as the Norse adapted and survived. They hunted seals and whales, wore fur instead of wool, used kayaks instead of European boats. The same environmental changes that killed the Norse barely inconvenienced the Inuit. Adaptability determined survival. The civilizations that endure are those that can change, that can abandon practices that no longer work, that can adopt new methods even when they contradict tradition. The civilizations that fail are those that become rigid, that cling to established ways even as conditions change around them. This is not a moral judgment, it is a historical observation. The Norse in Greenland were not stupid or lazy. They were trapped in a cultural framework that prevented them from recognizing and responding to the threat they faced. Consider our own cultural framework. We have built a society around the assumption that electricity will always be available. Every aspect of modern life reflects this assumption. Our cities are not designed to function without power. Our food systems cannot operate without power. Our water systems, our communications, our transportation, our healthcare, all depend on the continuous availability of electrical energy. When someone suggests that this dependency is a vulnerability, the typical response is dismissal. Surely we would never lose power on a large scale. Surely the grid is more resilient than that. Surely someone has planned for this. The Norse probably said similar things. Surely the climate would not change enough to matter. Surely their cattle would always find pasture. Surely the trading ships from Europe would always come. They were wrong, we may be wrong too. The difference between us and the Norse is that we know the risk exists. We have scientific models that predict solar activity. We have historical records that document past events. We have engineering studies that identify vulnerabilities in our infrastructure. The Norse could not have known that a climate shift was coming. We know that solar storms have happened before and will happen again. Our potential failure is not ignorance but willful disregard. The decision to accept a known risk because addressing it would be expensive or inconvenient. Future historians, if they exist, will judge us by how we responded to the warnings we received. They will ask why a civilization capable of landing robots on Mars was unable to protect its power grid from a foreseeable natural phenomenon. They will wonder why societies that spent trillions on military hardware declined to spend billions on transformer protection. They will note perhaps with puzzlement that we had detailed knowledge of the Carrington Event and the Miyake Events and the Quebec blackout, and yet chose to remain vulnerable, or perhaps they will not judge us at all because there will be no historians to render judgment. That possibility is remote, but it is not zero. A severe enough collapse extended enough could result in a loss of continuity that takes decades or centuries to overcome. The skills that sustain modern civilization are not inherent. They are transmitted through education and practice. If the institutions that transmit them fail, if the practitioners die without successors, knowledge can be lost as completely as it was lost when the Library of Alexandria burned. The people who lived through the Bronze Age collapse did not understand what was happening to them. They experienced it as a series of local crises, each one seemingly manageable, until the accumulation overwhelmed their capacity to respond. We might experience a solar storm collapse similarly, not as a single dramatic event, but as a grinding deterioration. Each day a little worse than the last, each week bringing news of systems that had not been restored, regions that remained dark, populations that had not been resupplied. By the time the scope of the catastrophe became clear, the time for effective response would have passed. This is not prophecy, it is scenario planning. The purpose of examining collapse is not to induce despair, but to motivate preparation. The Norse might have survived in Greenland if they had learned from the Inuit. The Maya might have survived their drought if they had developed more resilient agricultural practices. We might survive a Carrington-class event if we harden our grid stockpile critical equipment and develop contingency plans that can actually be executed under conditions of infrastructure failure. The civilizations that vanished before us are not just historical curiosities. They are warnings. They tell us that collapse is possible, that it has happened to societies as confident and capable as our own, and that the preconditions for collapse are often present long before the collapse itself occurs. Whether we heed those warnings or dismiss them as irrelevant to our modern circumstances is a choice we're making collectively every day through our investments and our policies and our assumptions about the future. The sun does not know about the Maya or the Bronze Age or the Norse in Greenland. It simply produces solar storms according to the physics that govern its behaviour. But we know about them. We have the advantage of historical perspective that they lacked. Whether we use that advantage wisely remains to be seen. What they are not telling you. The European Space Agency conducted an exercise earlier this year that received almost no public attention. They simulated a Carrington-class event striking during a satellite launch operation. The scenario was designed to test response capabilities to identify gaps in preparation and to understand how quickly systems would fail under extreme space weather conditions. The results were not encouraging. Atmospheric swelling of up to 400% in the simulation would have dragged satellites out of their orbits. Communication blackouts would have made coordination impossible. Space debris tracking would have failed, raising the risk of collisions that could generate even more debris. The exercise was never meant to reassure anyone. It was meant to demonstrate how unprepared humanity remains. But you probably did not hear about this exercise. It was not widely reported. The implications were not discussed on evening news programs or debated by politicians. This pattern repeats across the space weather community. The information exists, the studies have been done, the risks have been quantified. Yet the public remains largely unaware that the greatest threat to our technological civilization comes not from foreign adversaries or economic collapse or climate change, but from a storm on the sun. Why the silence? Part of it is complexity. Space weather is technical, involving concepts like geomagnetically induced currents and magnetospheric compression that do not translate easily to headlines. Part of it is probability. Major solar storms are rare on human timescales, easy to dismiss as problems for future generations. Part of it is the uncomfortable nature of the risk itself. There is something deeply unsettling about the idea that our entire way of life could be disrupted by an event we cannot prevent, predict precisely, or adequately defend against. It is easier not to think about it. It is easier to trust that someone somewhere has the situation under control. Consider what we know and what we do not discuss. We know that the Carrington event occurred in 1859. We know that a Carrington-class event in 2012 missed Earth by approximately 9 days. 9 days. The rotation of the Sun placed the eruption in a different position, and the CME sailed harmlessly into space where Earth was not. Had the eruption occurred 1 week earlier, the impact would have been direct. The damage estimates range into the trillions of dollars. Some analyses suggest the recovery time would have been years. We know that high-voltage transformers are the critical vulnerability in the power grid. We know that there are approximately 2,000 of them in the United States. We know that they are not manufactured domestically in significant quantities. We know that the lead time for replacement is 18 to 24 months under normal circumstances. We know that the Federal Energy Regulatory Commission has identified 30 critical transformers whose loss could cascade into widespread failure. We know that some combinations of as few as 9 transformer failures could result in coast-to-coast blackout. What we do not discuss is why, knowing all of this, we have not stockpiled spare transformers. We have not hardened the grid at a scale commensurate with the risk. We have not developed rapid response capabilities that could restore power within weeks rather than months. The technology exists. The engineering solutions are known. The cost estimated at $10 to $30 billion to protect the entire national grid is a fraction of annual military spending. And yet, the money has not been allocated. The work has not been done. The utilities argue that the risk does not justify the expense. They point to the rarity of major events, to the protections already in place, to the warning systems that would give operators time to take defensive measures. These arguments are not unreasonable in a narrow cost-benefit analysis that discounts low-probability events, but they ignore the asymmetry of consequences. A transformer costs a few million. The economic damage from a prolonged blackout runs into trillions. The human cost, the deaths from dehydration from medical equipment, failure from societal breakdown, cannot be calculated in dollars at all. There are those who argue for preparation more urgently. The Congressional EMP Commission, established in 2001, produced detailed reports on the vulnerability of critical infrastructure to both solar events and deliberate electromagnetic attack. Their findings were alarming. Their recommendations were largely ignored. The commission was defunded and disbanded. Its former members continue to speak publicly about the threat, but their voices do not penetrate the political discourse with any consistency. The Department of Homeland Security classifies space weather as a significant risk event. NOAA operates the Space Weather Prediction Center, monitoring solar activity continuously and issuing warnings when conditions warrant. The infrastructure for awareness exists. What does not exist is the infrastructure for effective response. We can see the storm coming. We cannot prevent the damage it would cause. This is the thing they are not telling you. Not because it is secret, but because it is uncomfortable. We have built a civilization balanced on a knife edge, and we have chosen not to reinforce the handle because the knife has not fallen yet. We have data from tree rings showing that the sun can produce events 10 times more powerful than Carrington. We have engineering studies showing that the grid would fail under conditions far less severe than those historical maximums. We have economic analyses showing that the cost of hardening is tiny compared to the cost of failure, and we have done nothing meaningful with this information. The current Sunspot AR4294 may rotate across the solar disk without incident. The most likely outcome is that it produces some impressive flares, perhaps causes a few radio blackouts and eventually decays as all sunspots eventually do. Solar cycle 25 will continue toward its eventual minimum. Scientists will continue to monitor and warn, and the grid will remain as vulnerable tomorrow as it was yesterday, waiting for the storm that statistics guarantee will eventually come. Some will ask what individuals can do. The honest answer is that individual preparation has limited value against a threat of this magnitude. You can stockpile water and food. You can purchase solar chargers and hand crank radios. You can learn survival skills and develop community networks. These measures might help in a short-term emergency, might extend your buffer by days or weeks. But in a prolonged grid failure lasting months, individual preparation is insufficient. The scale of the system that sustains modern life cannot be replicated at the household level. What can make a difference is collective action, demanding that utilities and regulators take the threat seriously, supporting investment in grid hardening and transformer stockpiles, electing officials who understand infrastructure vulnerability and will allocate resources to address it. The solutions are not mysterious, they are political. They require choosing to spend money on prevention rather than waiting to spend far more money on recovery. The information in this video is not secret. It is publicly available in congressional reports, academic papers, insurance industry analyses, and government websites. Anyone who wants to understand the risk can find the data. What is lacking is attention, the collective recognition that this particular threat deserves priority among the many threats competing for limited resources. I'm not telling you that a Carrington-class event will happen tomorrow. I'm not telling you that AR4294 will produce a civilization-ending flare. The odds against any particular sunspot producing such an event are high. What I'm telling you is that the event will happen eventually. That when it does, our current infrastructure will fail, and that we have the knowledge and capability to prevent the worst outcomes, but have not chosen to use them. The sun does not negotiate. It does not consider economic arguments or political priorities. It produces storms according to the physics of magnetic reconnection and plasma dynamics. One day, perhaps soon, perhaps decades away, it will produce a storm aimed directly at Earth that exceeds our current capacity to withstand. On that day, everything we have discussed in this video will transition from speculation to lived experience. The question is whether when that day arrives, we will have used the intervening time wisely. Right now, the largest sunspot in 10 years is rotating toward the most geo-effective position on the solar disk. Right now, solar cycle 25 is demonstrating activity that exceeded every official prediction. Right now, space weather forecasters are watching their instruments with heightened attention, hoping the magnetic complexity they observe does not release in our direction. And right now, you know more about this situation than most of the people around you, because most of the people around you have never been told that their comfortable technology-dependent lives rest on assumptions the sun may not respect. What you do with this knowledge is up to you, but the knowledge itself is no longer something you can claim not to have. Closing. We've travelled a long way together, from the dark wound on the face of the sun to the tree rings that whisper warnings across millennia. We've imagined the first 48 hours of darkness, the moment when water stops flowing, the gradual unravelling of systems we never consciously think about until they fail. We have looked at civilizations that vanished before us and asked whether we have learned from their mistakes or are destined to repeat them. The sun continues its ancient work, nuclear fusion at its core magnetic fields, twisting and reconnecting at its surface plasma streaming outward in a wind that touches every planet in our solar system. It has been doing this for 4.5 billion years. It will continue for another 5 billion long after whatever trace remains of human presence has been erased. We are temporary guests in a cosmos that operates on timescales that dwarf our brief existence, and yet for this moment in geological time we are here. We are conscious. We are capable of understanding the forces that could harm us and potentially of protecting ourselves against them. The sunspot will rotate across the solar disk in the coming days. It may flare spectacularly, producing headlines and beautiful aurora photographs. It may decay quietly, its magnetic complexity gradually dissipating into the background noise of solar activity. Either outcome is possible. Neither outcome changes the underlying reality that the sun has produced Carrington events before and will produce them again, that our infrastructure remains vulnerable, and that the choice to prepare or not prepare remains in our hands. Tonight, if the sky is clear where you are, take a moment to look up. The same sun that warmed your face today is the source of the storms that threaten our technology. The same stars that dot the darkness produce the heavy elements that make up our bodies and our machines. We are part of a universe that creates and destroys with equal indifference, and our survival depends on understanding enough of its workings to navigate the hazards it presents. Thank you for staying with me through this journey. If this exploration has given you something to think about, if it has changed how you understand our place beneath the sun, I hope you will share it with others who might benefit. A like helps more than you might realize, telling the algorithm that this kind of content matters, that there are people who want to understand the forces shaping their world, rather than ignoring them. And if you have not subscribed yet, consider joining our community for future explorations of the science and mysteries that define our universe. As always, what we have discussed here represents current scientific understanding mixed with informed speculation about possible outcomes. The future is uncertain. No one can predict with certainty when the next major solar storm will occur, or exactly how severe its impacts will be. What we can do is learn, prepare within our means, and face the unknown with as much knowledge as we can gather. Wherever you are in the world, whatever time the clock shows as you listen to these words, I hope you find moments of peace in the days ahead. The universe is vast and sometimes threatening, but it is also beautiful beyond description. The same sun that could disrupt our technology also makes life possible on this small planet. We exist because of it. Even as we prepare for its occasional violence, sleep well, dream of stars and remember that awareness is the first step toward resilience. Good night.